Alright, here we go. My first crack at section 4.4. A lot of sections this summer. My first cracks haven't been really that great, and I've had to restart them. So hopefully I can get through this in one go, but who knows. The title of the section is called Implicit Differentiation. And it's used when the letter you want to differentiate, let me get this right spelled because I can't really spell it right now. So what we had been doing, let me talk about what we had been doing and compare it to implicit differentiation and try to distinguish the two. What we have been doing, we haven't even called it this, we've been doing explicit differentiation because the problem was either written in function notation or it was solved for a letter that we were taking the derivative of. So, like we've done derivatives something like this, y equals to 3x squared minus 10x. And you might have said either y prime equal to 6x minus 10, or in this section, you might wind up saying dy dx equals 6x minus 10. This was easy to do because y was solved for. Similarly, I could have written a problem like this. Y equals to 5t cubed minus 4t squared. And then you could say y prime equals 15t squared minus 8t. And if I wanted to use this kind of symbol for this derivative, it probably wouldn't be right to say dy dx. There isn't an x in the problem. And it'd be more appropriate to say dy dt equals 15t squared minus 8t. When we do explicit differentiation, we usually have y solved for. And if I'm using the longhand notation, I read this as the derivative of y with respect to x is 6x minus 10. I read this as the derivative of y with respect to t is 15t squared minus 8t. Both of these explicit differentiations are somehow shortcuts, and we skip something that's not necessary. And when we do these derivatives, we don't really probably explain them well enough to make the connection to this section. So I'm going to try to do these two problems with the goal of making the connection to this section. So this problem that I wrote, y equals 3x squared minus 10x, and I took its derivative. What I'm really doing is taking the derivative of every single term. This y is a y to the first power, and if I take the derivative of y to the first power, I bring the 1 out front, I lower the exponent by 1, and the proper thing to do now is to say explain what I've done. I've taken the derivative of y with respect to x because the equation is set y equal to a function of x. In this part right here, this 1y to the 0 is just going to be 1 times 1 dy dx, and you get the dy dx. If I had been doing the same thing with the x's, this section would be easy. So when I take the derivative of 3x squared and I get 6x, what I really should do is I should explain what I've done. I've took the derivative of a term that had an x with respect to x. So I should tack on a dx dx, but dx dx, they cancel, they're equal to 1. So that's just 6x. Similarly, the derivative of minus 10x is minus 10, and I should explain that the term that I took the derivative had an x, and I took the derivative with respect to x. And again, that dx dx is equal to 1 because they cancel each other. So had I done the derivative that way, it might be easier to make the transition to this section. Let me do this problem that way. So I have the same function that I found the derivative of, and I'm going to do it the really long way. So the long way to do a derivative, in some sense, is going to be the best way for this section. So I'm going to take the derivative of y. It's y to the first power, so I'm going to bring the exponent out front, leave the y, lower the exponent by 1, and then because I took a derivative of the letter y, I'm going to make a fraction that has a dy in the numerator, and then because it's a function that's in terms of t, I'm going to explain that the y is solved for in terms of t. So I'm going to get a dy dt. And then on the right side, the derivative of 5t cubed is 15t squared. And again, I'm going to make a fraction, and the numerator is going to be a d with the letter that I have, and the denominator is going to be what the equation is solved for in this case, which is another dt. So those dt's are going to cancel. The last piece, I'm going to do the derivative of negative 4t squared, and that's going to be a negative 8t, and then I'm going to tack on the fraction. In the numerator, it's going to be a d with the letter that the function had that I took the derivative of, which is the dt, and the denominator, I'm taking the whole derivative with respect to t because it's y as a function of t. This is all going to simplify nicely because this piece is equal to 1, so the left side comes out to dy dt, and both of these are equal to 1, and the right side is going to come out to be 15t squared minus 8t. This is still really doing explicit differentiation because the equation was solved for y. We use implicit differentiation when the equation is not solved for the letter I need it to be solved for. So explicit, I did all of these using explicit differentiation. I needed all of these to be solved for y to find my dy dx or my dy dt. So, but when the equation, we'll say it's not solved for y, we have to use implicit differentiation. And if we take all our derivatives using this strategy, then implicit differentiation is not going to be terribly hard. It might make it a little bit longer, and eventually, once we get good at this, we'll stop adding the fraction that's equal to 1 because it's not necessary. So let me jump into the section kind of with this as a basis. And we're going to do implicit differentiation. Every problem that wants me to find a derivative in this section isn't solved for the letter I need it to be solved for. So when I look at problem 2, the instructions in section 4.4, the instructions say use implicit differentiation. I'm trying to find dy dx. The reason I'm going to use implicit differentiation as opposed to explicit differentiation is because the equation wasn't solved for y. I could just minus 4x squared from both sides and do explicit differentiation. So 2 can be solved using explicit differentiation. The only thing I would have to do is I'd have to rewrite it. I just can't spell differentiation right now. Differentiation. I'll just write sloppy so you can't tell that I can't spell it right now. So if I just took this 4x squared and moved it over and rewrote the problem as y equals negative 4x squared plus 3x minus 2, then I could do explicit differentiation, and then I could just do a regular derivative. The derivative of y is generally 1, because it's 1y to the first, so I'm going to go bring the exponent down, lower the exponent by 1, tack on the fraction that I said I took the derivative of a function that something that had a variable y, and with respect to x, because I'm told to find dy dx. To the right of the equal sign, each of the derivatives I'm going to do, at least these first two derivatives, I should tack on a dx dx because I'm taking the derivative with respect to x and the term has an x term on it. So this right here is going to be negative 8x and then dx dx. The dx dx isn't necessary because it's equal to 1. The derivative of this is going to be a positive 3. The term that I took the derivative of had an x, and I'm taking my derivative in terms of x. So this is going the left side is going to give me 1 times 1 times dy dx, so it's going to give me dy dx. And I'm going to get negative 8x plus 3 because that's equal to 1 and that's equal to 1. If you're taking the derivative with respect to x, like we generally do, then you don't have to tack on the dx. If you're taking if what you're asked to take the derivative in terms of the denominator here, that those terms with those letters don't need the extra piece because the extra piece is equal to 1. But you can always add that extra piece, but it's just because it makes a nice connection between what we're doing and what we need to do. And as the problems get more complicated, having this kind of in the back of your mind is going to make the rest of the section go smoother. At the beginning, it's going to make the beginning of the section go slow. And eventually, real quickly, I'm not going to write the piece that I don't need. So I used explicit differentiation. If the equation is solved for y and you're trying to find dy dx, then you're doing explicit differentiation. I shouldn't have written y prime there because that's just equal to y. That's not the derivative yet. Because I didn't take the derivative, I just rewrote it. And rewriting a function by moving it over is certainly not taking a derivative. So I should have y equals and not y prime equals. And in this section, I'm not going to use the y prime shorthand for derivatives. I'm going to use all the dy dx's because I'm going to need it in my algebra, and it's going to make the next section a little bit easier to follow. So this was explicit differentiation. To do this with implicit differentiation, I'll just leave the problem how it's written, take the derivative of each piece. The derivative of 4x squared is 8x, make a fraction. The letter that the term had that I took the derivative of had an x, and I'm taking all my derivatives with respect to x. The derivative of y is just like the derivative of x. The derivative of y would just be 1. I did it down here longhand, but I don't need to do it longhand. And then I have to emphasize the letter of the term that the term had was y, and I'm taking the derivative with respect to x. To the right side of the equal sign, the derivative of 3x is 3. Form a fraction. The numerator of the fraction goes a d with the letter that the term had. The denominator of the fraction is what you're taking the derivative in terms of, in this case, in terms of x. So this is going to give me 8x plus 1 dy dx, so just dy dx, equals 3, because each of the dx dx's are equal to 1. And I'm just going to minus 8x from both sides. And I'm going to get dy dx equals either 3 minus 8x or minus 8x plus 3. It doesn't matter. If you would have written 3 minus 8x, it would be completely correct. So that's using implicit differentiation, and the only reason this is different than this, because the equation wasn't solved for y, if I didn't want to take the time to solve it for y, then what I'm doing is doing implicit differentiation. And the only thing different between implicit differentiation and explicit differentiation really is how you treat the y. You're gonna need to tack on a little extra when you take the derivative with a y to tell me that I'm taking the derivative of y with respect to x. The x terms, if I'm taking the derivative with respect to x, I really don't need the extra fraction because the extra fraction is going to be equal to 1. And I don't even know if I even mentioned the derivative of that minus 2 was 0, but it was. So somehow for number 1, you need to get dy dx solved for. You could use implicit differentiation if you left the problem the way it was written. You could use explicit differentiation if you minus 3x from both sides. Eventually, it's going to get hard to do explicit differentiation because it's going to take a monstrous amount of work to solve an equation for y. So problems 3 and 4, I could do explicit differentiation. On my problem 4, I'd have to minus 4x cubed from both sides and then divide everything by 7. So to do explicit differentiation, I'd have to go 7y equals minus 4x cubed plus x squared plus 5x minus 3, and then I'll divide by 7, everything by 7, get y equals negative 4/7 x cubed plus x squared over 7 plus 5x over 7 minus 3 over 7. If I took the time to do this, then I could do explicit differentiation. But that's a nasty looking problem. It's not that hard to find the derivative, but it's not that nice to find the derivative. This is a nice polynomial without fractions. It's better to find the derivative. Easier for me to find the derivative of the problem how it's written than the rewrite of the problem. So I'm going to use implicit differentiation because I'm trying to find dy dx and my equation's not solved for y. So I'm going to take the derivative of every piece regularly, and I'm going to tack on the dx that I need to tack on. And then eventually, I think starting with the next problem, I'm only going to tack on the dy dx. So the derivative of 4x cubed would be 12x squared. And then I need to tell myself the original term had an x for its letter, and I'm taking the derivative with respect to x. Bring down my plus sign. The derivative of 7y is just like the derivative of 7x. It's 7. Now I have to tell myself the term had the letter y, and I'm taking the derivative with respect to x. Go to the right side of the equal sign. The derivative of x squared is 2x. Tack on the fraction. The letter that the term had was x, and I'm taking a derivative with respect to x. Bring down my plus sign. The derivative of 5x is 5. The letter the term had was x, and I'm taking the derivative with respect to x. So all the denominators are dx's because I'm taking the derivative with respect to x. All of the numerators are the letter that the term had. This last constant has a derivative of 0, so I don't need to worry about it. Well, this doesn't look very good, so let me get rid of these dx's because they're equal to 1. So now I have something a lot cleaner, but it's not done because I want to know what dy dx is, which means I need to solve for dy dx. So I'm going to minus 12x squared from both sides. I'm going to get messy if I keep going down here. So I'm going to make the left side 7 dy dx equals negative 12x squared plus 2x plus 5. I'm almost done. I can get what dy dx is. That dy dx is being multiplied by 7, so I'm going to have to go through and divide by 7 to know what dy dx is. And then because of all the fractions on the right side, we have some flexibility in terms of how we write our answer. So for number 4, I can write for my answer dy dx and just make it look just like it looks. Negative 12x squared over 7 plus 2x over 7 plus 5/7. That would be completely fine. This form, if I had to take another derivative, like a second derivative, it's maybe not the best form. And if I want to, these letters I can move out in front of the fraction and get an answer that's equivalently correct and probably easier to do a second derivative of if I had the need to do a second derivative, which I don't have the need here. So both of those would be perfectly good answers for number 4. Your problem 3 is a lot like my problem 4. My problem 4 looks like it was a little bit harder. And I would recommend using implicit differentiation because to solve for y, eventually you're going to have to divide by 3. To use explicit differentiation, you have to isolate the y, which would involve dividing by 3, which would introduce fractions a lot earlier than they need to be introduced. Using implicit differentiation, my answer had fractions, but I didn't need to do any algebra with any nasty fractions. So for the rest of the problems in this first group, anytime I take a derivative with respect to x of a term that has an x, I'm not going to tack on the dx, even though it might be nicer if I did just to drive that point in, but I'm going to be lazy like we have been and not put that in. So problem 6, it would be a monster to solve this for y. I'd have to move the 6x squared over, I'd have to divide by 5, and have to do the cube root. That's way more work than I want to do, so I'm going to use implicit differentiation. The equation's not solved for y, but I can still find dy dx. So I'm going to do the derivative of each of the 4 terms, and for this, because I'm taking the derivative of a term that has a y, I really do have to put on the dy dx part. These terms, that I'd have to put a dx with. This I'd have to put a dx with. Those aren't really necessary because they're equal to 1. And that 4 has a derivative of 0, so it's not really that interesting. So let me work on my derivative. So the derivative of 5y cubed would generally be 15y squared, and I need to emphasize that the term had a letter y, and I'm taking the derivative with respect to x. The derivative of 6x squared is 12x. If I was to add a fraction to this, the numerator would be dx because the term has the letter of x, and the denominator is dx because I'm taking all the derivatives with respect to x. Now I'm going to bring on my equal sign. The derivative of 4 is 0. I won't worry about it. The derivative of minus 3x is minus 3. And again, if I want it to be proper, I would tack on a dx in the numerator because the term has a letter x, and in the denominator another dx because the instructions say take the derivatives with respect to x. So I'm almost done. I just need to get this thing solved for dy dx. So I'm going to minus 12x from both sides. That's going to give me 15y squared dy dx. And I go minus 12x minus 12x. And that'll give me minus 12x minus 3. If you feel the urge, factor out a minus 3. That's not completely necessary. We're not doing anything with the derivative. I think just having the derivative solved for dy dx would be enough. And to get dy dx solved for, I need to divide by 15y squared. The easiest way to divide by 15y squared would be divide both sides like that by 15y squared. You could, however, on the right-hand side, divide each term separately by 15y squared. And you'll get the same answer, or an answer that's equivalent to your answer. It might look slightly different. So on my left side now, I have my 15y squareds cancel, and I have my dy dx that I'm shooting for. Now on my right side, I probably should reduce this. If you miss the factoring and canceling that can be done, I'd probably write it in on a test and not take points off. But there's certainly a common factor of negative 3 in the numerator I could factor out. When I factor out a negative, I flip the sign, so I'm going to divide by 3 and flip that to a positive and get a positive 4x. I'm going to divide that by 3 and flip the sign to a positive and get a positive 1. Now, this negative 3 and that 15 will cancel. Negative 3 divided by negative 3 is 1. 15 divided by negative 3 divided by 3 is negative 1. 15 divided by 3 is 5. And the best answer for problem 5, problem 6, actually has a y in the answer, which is unusual, but it's okay, because I'm only asked to find dy dx, and I've done exactly that. The instructions for each of the first group of problems say find dy dx, and it doesn't say I can't have a y in my answer. And sometimes you just can't avoid that. When the equation is kind of ugly like this, you're almost locked into getting a y. All right, we'll keep going. So give number 5 a go. And the next problem looks lovely. We'll try to see what happens with it. So 7 and 8 have ugly fraction exponents. Usually we turn fraction exponents into radicals. Definitely if the problem was presented with radicals and I changed the radicals to fraction exponents, then I want my answer to be in radical form. But because I wrote the problem with a fraction exponent, I'm going to say it's okay to have my answer with a fraction exponent, just won't have negative exponents. And I'll show you how to change the answer to radicals, but if the initial problem was written without a radical, you don't have to push a radical into your answer. So now I'm going to do the derivative of every term. The derivative of x to the 3/4, I'm going to bring the 3/4 out front, and then I'm going to take the exponent and lower it by 1. And to lower the exponent by 1, I'm going to have to minus 4/4. If I wanted to, I could tack on a dx dx because the term had a letter of x. I'm taking the derivative with respect to x, but dx dx is equal to 1, so I don't need to worry about it. For the y, I'm going to do plus, and I'm going to bring the exponent down front and make it a 1/2 y. And I'm going to lower the exponent by 1, and in this case, I'm going to call that 1 2/2. And I absolutely have to tack on the dy dx because that's not equal to 1. So the term had a letter of y, and I'm taking the derivative with respect to x. And on the right-hand side, the 4 doesn't have a letter, so it has a derivative of 0. Let me clean this up a little bit. So I get 3/4 x to the negative 1/4 plus 1/2 y to the negative 1/2 dy dx equals 0. My goal is to solve for dy dx. Let me make those negative exponents positive. Make this 3 over 4x to the 1/4 plus 1 over 2y to the 1/2 dy dx equals 0. This is going to be a little bit messy. Next thing I'm going to do is minus this one. I'm going to minus 3 over 4x to the 1/4 on both sides. And when I do that, I'm going to get 1 over 2y to the 1/2 dy dx equals negative 3 over 4 times x to the 1/4 power. I need to get the dy dx solved for. There's a number that's in front of it that's a fraction. If you multiply by the reciprocal of this, so I'm going to multiply by 2y to the 1/2 over 1 on both sides. That's going to get the dy dx's out, because these two y's to the 1/2 will cancel, and those 1's, well, they cancel, but they stay 1's. But multiplying by the reciprocal of that fraction is going to cancel out what's in front of the dy dx. It's going to give me the dy dx, and now I'm going to, well, if I multiply this, I'm going to get negative 6 y to the 1/2 over 4x to the 1/4. I should probably reduce that fraction and make that 3/2. So I'm going to get dy dx equals negative 3/2. And then I can leave the y to the 1/2 and x to the 1/4, but it probably would be nice. 1/2 power always turns into a square root. 1/4 power always turns into a fourth root. So leaving the fraction exponents would be completely fine, because the original problem had fraction exponents. It's okay for my answer to have fraction exponents, but taking the time to write the radicals, it's kind of nice. All right, so your problem 7 should be just like my problem 8, with the same level of grunginess. I don't think mine's any harder or yours is any easier. They're about the same. Ten is where for me, it started getting hard, because there's a multiplication here that I'm going to have to use the product rule for. So when I go to do number 10, I'm going to have to use the product rule, and I have to be really careful when I use the product rule using implicit differentiation. So first I'm going to take the derivative of x cubed, and that's easy. That's 3x squared. Technically, I should say the term had a letter x, and I'm taking the derivative with respect to x, but that's equal to 1, so it's not necessary. The next piece, I'm going to do the product rule. And the product rule says first I have to do the derivative of the x times the y piece unchanged plus the derivative of the y times the x piece unchanged. So this right here is using the product rule to find the derivative of xy. To the right of the equal sign, I'm taking the derivative of a constant. It has the derivative of 0. Haven't even taken the derivatives I need to take here, so let me go ahead and take them. So I'm going to leave this as 3x squared. The dx dx is equal to 1, so I'm not going to write it. The derivative of x is just 1. And because I took the derivative with respect to x, I should put a dx dx there, but I'm just not going to, because it's equal to 1. And I'm going to bring down this y. I'm going to leave the times sign alone. I don't need that times sign. The derivative of y is just like the derivative of x. The derivative of y would be 1. Because I took the derivative of a y with respect to x, I have to tack on so for this term here, when I'm taking its derivative using, that's the second half of the product rule, I take the derivative of a y. The derivative of a y is just like the derivative of an x, which is 1. And I emphasize that I took the term that I took the derivative of had a y, and I'm taking the derivative with respect to x. And I finish up the product rule. This x part doesn't change. All right. So good enough. So now let me try to clean this up a little bit. I don't know. It's going to be much cleaner. I'm going to write 3x squared plus y equals x d plus x dy dx equals 0. I don't need the 1 there, and I multiplied the 1 and the x, and I wrote the x first. So I need to solve for dy dx, and to solve for dy dx, there's some subtracting I have to do. I'm going to minus 3x squared and minus y from both sides. When I do that, the left side's going to leave me x times dy dx, and the right side's going to give me minus 3x squared minus y. You could factor out a negative 1 if you really care to, but you don't have to. And now I'm going to need to divide by x to solve for dy dx. And when I go to divide by x, I could write x under each term, and if I do that, my answer will reduce. If I would have done on the right side one big fraction, this doesn't reduce, at least without separating it into two fractions. So it would be fine if I wrote dy dx equal to this, because when you divide both sides by x, on the left side, when you divide by x, you're left with a dy dx. And then on the right side, you could make one fraction with the binomial in the numerator and the x in the denominator. That can't be reduced the way it's written. Or you can make two fractions, and if you take the time to make the two fractions up, then the first fraction you can cancel out an x, and you're going to get minus 3x minus y over x. So these are both okay answers. The one on the right is probably the safer way to go, because you're not because it's legal to reduce. And the one on the left, a lot of students will reduce this, and they'll write something like minus 3x minus y equals dy dx. But that x needs to remain under the y. So you can't reduce the x squared with the x without leaving the x under the y. So that would be a wrong answer. All right, so there's your problem 9 to give a go. Section's taken a good long time, and it's a long section. We've had a lot of short sections in this chapter, and this is not the one. This is a monster. All right, so I'm going to do 12. So problem 12 is x cubed plus xy cubed equal to 3. The derivative of x cubed is 3x squared when I'm taking the derivative with respect to x. The next term has multiplication, so I need to use the product rule. So I'm going to take the derivative of the x times the y cubed, how it was written, plus the derivative of the y cubed times the x unchanged, equals, and on the right-hand side, the derivative of 3 is 0. So I actually took two derivatives and sketched out the template for the product rule. So now I'm going to get 3x squared plus the derivative of x is 1 times dx, so it's just 1. So that's going to be 1y cubed. The derivative of y cubed is 3y squared, but because I took the derivative and the term had a y, and I'm taking the derivative with respect to x, I have to tack on a dy dx, and then I leave this x equals to 0. Let me clean this up by moving the x in a nicer spot and getting rid of that 1. So I get 3x squared plus y cubed plus 3xy squared dy dx equal to 0. And it's almost exactly the same now. My solving is going to be real similar. I'm going to minus 3x squared and minus y cubed from both sides. And when I do that, I'm going to get a 3xy squared dy dx equals minus 3x squared minus y cubed. Now I need to divide by the number that's in front of the dy dx, and I'm going to make two fractions on the right hand side as opposed to making one big fraction, because it makes the reduction easier and it makes it so I can reduce. So on the left side, when I did this division, I cancel everything out. I get the dy dx that I'm shooting for. On the right side, this first fraction, the 3's cancel and come out to a negative 1. I have 2 x's in the numerator, 1 in the denominator. I'm going to cancel the x in the denominator with one of the 2 x's in the numerator. I'll be left with a 1x in the numerator and a negative 1. In the denominator of this term, the y squared is going to hang out. I'm going to bring the minus sign, and for this fraction, this y cubed and that y squared cancel. When there's 3 y's in the numerator and 2 in the denominator, when you cancel, you're left with 1 y in the numerator, and I have the 3x that's still left in the denominator. That's a perfectly good answer. You could have this term written as negative x over y squared, if you care to. But you don't have to. It's completely fine the way it was written initially. All right, so you should be able to do number 11. It's very similar. So far, each of the problems have only had one y. And I mean, the algebra has gotten messy, but not as messy as it's going to be when the problems have 2 y's, and that's coming up next. Yuck. Oh my gosh. I got a little carried away here. How many of these do we have? Okay, so we go up to 24. So we have like 5 or 6 more of these to go. So for problem 14, there are 2 y's, and that's unfortunate. So the derivative of x cubed is 3x squared. I could tack on a dx because the term had an x, and I'm taking the derivative with respect to x, but it's not necessary. The middle piece here, I need to use the product rule. So I'm going to take the derivative of the x times the y unchanged, plus the derivative of the y times the x unchanged. Haven't taken any derivatives yet, so I haven't tacked on any dy dx's. And on the right-hand side, the derivative of 3y would generally be 3, just like the derivative of 3x would be 3. And I emphasize that the term had a y, and I'm taking the derivative with respect to x. Almost done. No, I lied. That's way from being done. Dx is equal to 1. I'm not going to write it. Here, the derivative of x is 1. I should tack on a dx, but that's not really necessary. The derivative of y is 1. I do need to tack on the term I took the derivative of had the letter y. I'm taking the derivative with respect to x, and I leave this x. So just like since I started with 2 y's, my work ended up with 2 dy dx's. In order to handle this problem, I need to get the terms with the dy dx's on the same side of the equation. So I'm going to minus this 1 dy dx x from both sides. So, and I'm going to write it as minus 1x dy dx. Don't even need the 1, but the x feels like it should be over there. So when I subtract it from both sides, the left-hand side gives me a 3x squared plus 1y. I'm just going to write a y. And on the right-hand side, I have a 3 dy dx, and now it's going to be a minus 1x dy dx. So there's a common factor of dy dx on the right side, and I'm going to factor it out. I'm going to leave the left side 3x squared plus y. And on the right side, I'm going to go dy dx times 3 minus 1x. Don't need the 1 in front of the x, but it's certainly okay to have it. And now I'm going to solve for dy dx. And because there's something multiplied by the dy dx, I'm going to divide by it. And it's not so tempting now to reduce. I could write that 3 minus 1x over each of the terms, but nothing's going to reduce. When you're dividing by a binomial, you might as well just put the whole side over that binomial. Here now on the right-hand side, everything cancels, and I'm left with my dy dx, and that's what I'm trying to solve for, because my instructions said find dy dx. And on the right-hand side, the fraction doesn't reduce. You could leave that as your answer. If it bugged you, you could write the negative x first. In the 3 second, you could factor out a negative. There's lots of things you can do to make something equal to this fraction. This fraction for an answer would be okay. This is okay. Any variation of this where you factor out a negative 1 also would be okay. Alright, so your problem 13 should be a lot like my 14. I always try to make our even and odd problems, basically the same. I just think I wrote too many of these problems. I'm wearing out. Alright, 16. x cubed plus xy cubed equals 3y cubed. The derivative of x cubed is 3x squared. If I wanted to, I could say it's dx dx because the term that I took the derivative of has the letter x. I'm taking the derivative with respect to x, but that's equal to 1. I won't write it. Here I need to use the product rule. The product rule will say I'll take the derivative of the x times the y cubed unchanged plus the derivative of the y cubed times the x unchanged. That's not done yet, but that's how that's going to go with the product rule. And then the derivative of 3y cubed is going to be 9y squared. And then again, I have to say I took the derivative of a term that had a y with respect to x. All right, let me finish up this derivative. The derivative of x is just 1, so that's going to be a 1y cubed. And then plus the derivative of y cubed is 3y squared dy dx. And I bring down this x. Wow. So I have, let me try to write this better, 3x squared plus y cubed plus 3xy squared dy dx equals to 9y squared dy dx. Again, I have two dy dx's, so I need to get them on the same side of the equation. I'm going to minus 3xy squared dy dx from both sides. And when I do that, the left side gets really nice. The left side's just 3x squared plus y cubed. And the right side now is going to be 9y squared dy dx minus 3xy. Oh gosh. So what happens when you write crappy. The left side is going to be, the right side is going to be 9y squared dy dx minus 3xy squared dy dx. Although there's a big common factor, I could factor out a 3, I could factor out a y squared and a dy dx. Factoring out any more than a dy dx is not going to help. So I'm only going to factor out a dy dx on the right side, even though there's a bigger common factor than that. The reason I don't factor out more at this point is because it'll make it very hard to solve for dy dx. If you only factor out the dy dx, then you can divide by what's left. So I'm going to divide both sides by 9y squared minus 3xy squared and 9y squared minus 3xy squared. This is going to cancel. If I left the left side like this on a test, I'd be completely happy with that. There is a common factor in the denominator that might be tempting to factor out. It would be kind of nice if you factored it out. But when you factor it out, it doesn't cause any canceling to happen. And I didn't write each term separately over the denominator because it's a binomial. And generally, you're not going to cancel monomials with binomials. So when I'm dividing by a term that has a plus or minus between it, I never make the two fractions up. I just do the one fraction. So probably this would be okay for an answer, and what I'm going to write now is probably slightly better. I'm going to factor out a 3y squared, and we'll be left with 3 minus x. Still, these 3's don't cancel, those y squareds don't cancel. So because nothing cancels, if you miss the factoring that can be done, it's not such a big deal, especially because we're not doing anything but finding a derivative. If I was using the derivative to do something, then maybe I'd want to do more. All right, so both of those are okay for the derivative. If you catch the common factor, fine. If you don't, I'm not going to take points off. I might write it in on the test if I feel the need to, but I won't take points off. When you're doing implicit differentiation, and if there's a common factor in the derivative and doesn't lead to any canceling, you're not going to lose any points for missing that. All right, 15 is about the same. So 5 more problems, 14 minutes before the video ends out again. Let's see what oh gosh. Ugh. All right, so let me try this. This is really not so nice. Wasn't ready for that. I almost wanted to hide it. So when you take the derivative of an e, you take the e function and you multiply it by the derivative of its exponent. The derivative of 2y is the tricky part of this. So for the derivative of the e function, you always get the e function back. So this e function is going to come back, and right to after the 3, before the e to the 2y, I'm going to put the derivative of the exponent. The derivative of 2y is just 2, but because I took the derivative of a y, the term had a y, and I'm taking the derivative with respect to x. So I tack on a dy dx. So the very first term has a derivative of 6 for the 3 times 2. It has an e to the 2y, and it has a dy dx. The derivative of x squared is just 2x. The derivative of 5x cubed is 15x squared. So there's my derivative. It's not solved for dy dx, but there's only one dy dx, so it's not going to be that hard to finish this up. So I'm going to minus 2x from both sides and then get 6e to the 2y dy dx equals 15x squared minus 2x. You could definitely factor out a common factor of an x from that numerator if you care to. Now to get the dy dx solved for, I need to divide both sides by 6e to the 2y, which is the thing that was multiplied by the dy dx. So now I'm going to get dy dx equals, this would be okay for the right side for an answer. Because there's a common factor, I just have the urge to factor it out. I'm going to factor it out. But you can't do any canceling. You can't cancel the 6 with the 2 nor with the 15. And then e to the 2y is definitely not going to cancel with anything. So had you written that for an answer, or this for an answer, they'd be completely fine. Your problem 17 should be just like my problem 18, so give it a go. Really? Alright, I'm definitely wearing out on this, and they're not ending. We have 3 more problems in this grouping, and there's more to the section that we'll do in a part 2 of a video. So how do I do the derivative? Same way. This 3e to the 2y, I leave the 3 and the e to the 2y where they were. In between them, I'm going to write the derivative of the exponent. The derivative of 2y is generally 2. I need to tack on that I took the term had a y, and I'm taking the derivative with respect to x. The derivative of x squared is 2x. If I wanted to, I could tack on the term had an x, and I'm taking the derivative with respect to x, but that's equal to 1, so it's not really necessary. The 5y cubed has a derivative of 15y squared, and the term had a y, and I'm taking the derivative with respect to x, so I have to add the dy dx on. So now I have 6e to the 2y dy dx plus 2x equals 15y squared dy dx. And when you have 2 dy dx's, you have to get them on the same side of the equation so you can factor out a common factor. So what I'm going to do is subtract the 6e to the 2y dy dx from both sides. On the left side, that cancels, but the 2x hangs out. On the right side, now I have 15y squared dy dx minus 6e to the 2y dy dx. There's actually a common factor with a 3 and a dy dx. Again, because I'm trying to solve for dy dx, I'm only going to factor out the dy dx. From the first term, when I factor out a dy dx, I'm left with a 15y squared. From the second term, when I factor out a dy dx, I'm left with a 6e to the 2y. And now I'm going to divide by 15y squared minus 6e to the 2y on both sides. On the left side, I get this ugly thing. On the right side, it cancels. This would be an okay answer. The denominator has a common factor of 3 that you could factor out. If you factored it out, you'd have 2x over 3 times 5y squared minus 2e to the 2y equals dy dx. Both of these, the circled answer or the factored version would be fine. Neither one of them reduce, and when the factoring doesn't lead to any reducing, then it's not such a big deal whether you factor it or not. So give 19 a go. 9 minutes and 3 problems. I think I can get them in, and then we'll do a part 2 of the video. All right, so 22 has this ugly radical that I need to change to a fraction exponent. So that square root of y I'm going to write as y to the 1/2. Now I'm going to do the derivative. For the derivative of y to the 1/2, I'm going to bring the 1/2 down front. I'm going to lower the exponent by 1. And because I took the derivative of a y with respect to x, I tack on the dy dx. This piece I need the product rule. So it's going to be the derivative of 4x times the y plus the derivative of the y times the 4x. And then to the right of the equal sign, the derivative of 3x squared is 6x. Ugh. So this is going to give me 1/2 y to the negative 1/2 dy dx plus the derivative of 4x is 4. I bring down the y plus the derivative of y is 1. I tack on the dy dx and leave the 4x. Let me clean these up a little bit. Here I'm going to multiply these, and I'm going to make a positive exponent out of this. So I'm going to get 1 over 2y to the 1/2 dy dx. Let me minus 4. Oh heck, I can't combine those. Those are separate terms. Let me minus 4y from both sides too. That's going to give me, on this side, those will cancel. And I'm going to clean this up. I'm going to write this as 4x. Sorry, 4x dy dx. So what I'm doing is a couple things at once. So I cleaned this up by making the negative exponent positive. This piece didn't have a dy dx, so I minus it from both sides to get it on the right side. And this piece, I multiplied the 1 and the 4x and got a 4x. Now I have a lovely common factor of dy dx that I'm going to factor out. When I factor it out, I have 1 over 2y to the 1/2 plus 4x, and then equals 6x minus 4y. You can certainly factor out a 2 from the right side. And now I'm going to divide by this, and I'm not going to make any efforts to clean that up. You certainly could make this into one term. It would be a monster, ugly problem to do. I should probably write that with a square root sign, and I should probably factor out a 2 from the numerator. But if you had this as your answer, I'd live with it. A better answer would be dy dx equals 2 times 3x minus 2y over, and I'm not making any efforts down here. I don't need a parentheses in the denominator, but I'm going to go 1 over 2 square root of y plus 4x. That's a really ugly looking answer. It certainly can be written a lot nicer, but there's no point in making it look nicer. I did the common factor factoring, and that seems like enough. So give 21 a go. You should get an answer that's probably equivalently ugly as my answer. And now I'm going to do the last problem for this video, and then part 2 will have the rest. All right, so 24. X squared e to the 2y plus 3y squared equal to 5x. Need the product rule here. So I'm going to do the derivative of x squared times the e to the 2y plus the derivative of e to the 2y times the x squared, and then plus the derivative of 3y squared is 6y. I tack on my dy dx because the term had a letter of y, and I'm taking the derivative with respect to x. And then to the right of the equal sign, the derivative of 5x is 5. So I haven't taken all the derivatives. I need to finish up this product rule. The derivative of x squared is 2x, so I'm going to leave that first term as 2x e to the 2y. The derivative of e to the 2y would generally be just 2e to the 2y, but because I took the derivative of the exponent, which has a y, I need to tack on a dy dx. and then I'll leave the x squared there, and then I'm leaving everything else the way it is. So now I've taken all the derivatives. I need to get the term that doesn't have the dy dx on the right side by minusing it from both sides. When I do that, I need to also clean up the left side. So I'm going to rewrite this term with the x squared kind of moved over. So that term that I didn't move, I moved the x squared over, wrote it as 2x squared e to the 2y dy dx. I'm going to leave this term 6y dy dx. Yuck. And on the right side, I'm just going to write 5 minus 2x e to the 2y. At least there's no common factor there. If it bugs you that the variable is written second, you can write the 5 second. Now on the left side, I'm going to factor out a dy dx. When I factor it out, I have a 2x squared e to the 2y plus 6y. And now my right side is 5 minus 2x e to the 2y. At the minimum, I just need to divide by this nasty thing in the parentheses on both sides. That's 2x squared e to the 2y plus 6y. 2x squared e to the 2y plus 6y. If this is what you wrote for your answer, it's fine. There is a common factor of a 2 in the denominator I could factor out. So probably better if I would write dy dx equals 5 minus 2x e to the 2y over 2 times, and then if I factor out a 2 from that piece, I'm left with x squared e to the 2y. And if I factor out a 2 from there, I'm left with plus 3y. Both this or that for your answer would be completely fine. So give 23 a go. The next problems, well, they're just different. I don't know if they're easier or harder, but I think they're easier. But they're more involved. But there's more steps, but I think the derivatives are easier. So this is going to be the end of part 1. There's going to be a part 2, but there won't be a part 3.